Okay, well, I'm going to talk about the data from the LEND instrument. As we all know, quite some while ago, a little over a decade ago, Lunar Prospector found a very significant depression of epithermal neutrons in the polar areas, which is indicative of enhanced amounts of hydrogen being present. At the time, the prevailing wisdom was that this hydrogen was located in the permanently shadowed regions, the floors of various craters and so forth. And the LEND instrument was actually designed using collimated detectors so we could get much better spatial resolution, so we could actually see if indeed the hydrogen was located in the permanently shadowed regions, and if not, where was it located. These are some maps of the LEND data. This is the North Pole, the South Pole. The neutron suppressed regions, as we call them, are areas where the neutron flux, epithermal neutron flux, is substantially lower than the surroundings, and this indicates an enhancement of the hydrogen. You can see that we have a dynamic range here of about 0.2 counts per second, maybe a little bit more in the south. This is the same map in the south, except now we've added some of the larger of the permanently shadowed regions. You can see that the crater Shoemaker has a NSR right smack dab in the middle of it, but another PSR right nearby has no neutron suppressed region at all in it. There's a hint of one outside it, but it's really absent here, and maybe a small amount of neutron suppression in Faustini. Cabeus, as we know, also has a NSR associated with it, but it's actually larger than the PSR itself. This is something that's been known for a while. One of the things that we should take away from this is the fact that's been mentioned before, that the NSRs and the PSRs really are not closely related. Some of the NSRs are associated with PSRs, some are not, and vice versa. Some of the PSRs have an NSR in them, some do not. We can see that these are really statistically very significant. The Shoemaker depression is down by about 0.19 counts per second. We have a measure of the statistical uncertainty in the counting data here, and it's about 0.12, 0.012 counts per second. So it's about a 15 sigma event. These are really quite real suppressions of the neutrons. Okay, but as I mentioned in Igor's talk, there's been a lot of criticism of this instrument, and I really think it's important that we talk about it, get it out in the open, and I hope put this to rest. This paper was published around the time of the LRO launch. It was really very critical of LEND's expected performance. At the time this was published, LEND was just about to be launched, and we had calibration data, but no one really knew how well it was going to perform. This criticism has continued to this day, and the community is confused about it. For example, at the last Lunar and Planetary Science Conference, one very distinguished senior member of the lunar science community asked Igor following his talk, what about this controversy between Lawrence's work and the performance of this instrument? And Igor gave a quite well-reasoned response, very polite response, but in the end, this scientist who was questioning him said, yes, but who do we believe? Okay, well, it's important that we understand who can be believed here. So I'm going to talk about some of the models. Essentially, in their models, calculations based on the construction of the instrument, and they felt the count rate would only be about 0.18 counts per second of the counts actually coming through the collimator. Turns out they're off by nearly an order of magnitude. There'll be a talk on Thursday where Segdeyev is going to show why the count rate is really on the order of 1.5 counts per second coming through the collimator. Lawrence also claimed that a very large fraction of the lens counts would come through the walls of the collimator, and indeed there are a fair number that do come through the walls of the collimator, but said that the lens maps should look very much like those of Lunar Prospector. Well, they don't. And again, that's part of what I'll be talking about here. It's important to put these criticisms to rest. One of the things I just realized is that there's a poster here, E17, you can go look at it, and the allegation is made that the count rate is actually only 0.05 counts per second in the collimator. So that's the whole dynamic range of the instrument for the focus counts through the collimator would be just 0.05 counts per second. But you remember back here, we are seeing a dynamic range of 0.19 counts per second. Well, you can't do that if the full scale range is only 0.18 or 0.05. It would have to be 100% water ice if the full dynamic range were 0.19. It's in fact substantially greater than that. Okay. Okay, here's a plot of the flux depression near the Shoemaker crater. We saw a similar plot when I gave Igor's talk early in the morning. What's important again is to see that the spatial resolution is consistent with the small diameter of the Shoemaker crater, and the flux follows the topography of the crater quite well. Again, as I mentioned, there seems to be enhancement on the poleward facing side. We see this in other craters as well, and Tim McClanahan has talked about that in the past. Okay, talking about the background now. That issue came up this morning. It came up following the talk I gave here last year. When Dave Lawrence mentioned it last year, I said, you really don't have to worry so much about the background because it's going to be a large number, but it's not going to vary rapidly over small spatial areas. Over large areas, yeah, it'll vary a little bit. Anyway, we have some good laboratory data that was measured in the Institute for Space Research in Russia, and we actually used these laboratory data to calculate exactly what the leakage would be through the walls of the collimator, and we could make a background map. As an experimentalist, I think this is very important. Good data is worth 1,000 model calculations. It's really at this point straightforward once we have these data to determine the background contribution, and so that's what we've done. And indeed, this is what the background counts would be at any given location on the moon. So if the spacecraft were right here, this is what the background would be. If the spacecraft were here, this is what the background could be. So it is appreciable. It's about 1.7 counts per second out of the total 5 counts per second. But the total range over this whole area is only plus or minus 0.01 counts per second. And over small spatial scales, it's really very, very small. Here is that same count rate data for the Shoemaker depression. The one color is corrected and the other is uncorrected. You can see there's really a negligible difference between the two data sets. Okay, let's look at the Lunar Prospector data. Lawrence was saying that really this lens spatial resolution should not be much better than the Lunar Prospector data, but when you put Lunar Prospector on the same plot with the Shoemaker topography, it completely misses it. In fact, I had to expand the scale so you can see the big broad depression that's been there, that's been well known, but the sharp depression around Shoemaker just is completely absent. Again, if we put the lens data on the same scale, you can see that the lens data follows the topography really quite well. So the bottom line in all of this, and now we're going to get on talking about the science, but I apologize we had to have this aside, but it really is important that the community appreciate this instrument is working spectacularly well. The data is really exquisite, and it's time we get on to talk about the good science we can get from the instrument. Okay, Now we got 2 minutes to talk about the science. Okay. We've talked about this, the fact that the PSRs, the NSRs don't relate. We actually calculate this by looking at the difference relative to the surrounding materials. So the previous slide was absolute count rates. Now we're taking a difference map, and we take the difference relative to an annulus at the same latitude. In fact, here's a plot of all of the different annuli as a function of latitude, and you can see that the flux decreases as you get towards the pole, meaning the hydrogen is actually increasing. It's also of interest that we really have a bimodal distribution here. The NSRs are not just a tail of the distribution of what we're seeing with the normal distribution of hydrogen. It's actually a bimodal distribution, and so something different is happening to explain what's going on with the NSRs. In the past, of course, it was thought that was easy to explain. It's just we've got the permanently shadowed regions, but that's no longer a viable explanation that can explain all of the differences. It also was of interest that even when we take out the effect of the NSRs, we still see this increase in hydrogen as we go towards the poles. This was known before, but it was assumed that all of this increase was due to the permanently shadowed regions. Now we know that's not the case. When we take out the the NSRs, the neutron suppressed regions, we see that there still remains what we call a background increase in hydrogen towards the poles. To us, the fact that the hydrogen increasing rather linearly as you go towards the poles suggests it's probably not related to the solar wind, in this case, at least as the final distribution mechanism, but that the distribution is probably related to hydrogen migration controlled by temperature, because you would expect the temperatures to decrease slowly as you go towards the poles. So finally, in summary then, the NSRs and PSRs are not closely related. The NSRs are not the tail of a normal distribution. There's different processes going on that we have to be able to explain. Even when we, whoops, well, okay. I guess that's one way of telling me okay, even when we remove the hydrogen associated with the NSRs, we see this increase in hydrogen going towards the poles. It's the same in the North Pole and the South Pole. I mentioned the enhancement is more prominent in the poleward-facing side of the craters. That's another interesting observation. And finally, I do want to remind you, these observations, none of these would have been possible if it weren't for the fact that LEND is really performing exceedingly well. Thank you.
So, Vincent Eek, Durham University. So thank you for advertising my poster. I'm not sure you've understood it quite as it was intended, but...
I only looked at the bottom line of a 0.05 counts per second, which was wrong. I didn't pay attention to how you got there. It didn't matter.
Well, that's another assertion you're making. So you assert that the lunar collimated flux dominates the lunar uncollimated flux. Can you conceive of any test that could disprove this assertion? And if so, what is it?
The collimated flux and the uncollimated flux are comparable. What the important thing to take away from this is that the uncollimated flux is broad and diffuse. It's averaging the neutrons coming from about 500,000 square kilometers. The collimated flux is measuring over a very small area. So if we move from one very small area to another small area next to it, the background does not change, but we see a change in the collimated flux. That's the only way you can explain these very high spatial resolutions that we're seeing. The background is large, but it's essentially constant.
So in the Mitrofanov et al. Science paper, the lunar collimated flux is stated to be about 10 times as big as the lunar uncollimated flux. So that's different to what you've just said. You just said that they were about comparable. So I'm wondering what do you mean?
I'm sorry, I didn't understand the question.
So in the Mitrofanov et al. Science paper, it states that there's about 1.9 counts per second coming from the lunar in the collimated flux and about 0.2 in the lunar uncollimated flux. And
Okay.
you've just said that they were about the same.
Yeah, they are, actually, I misspoke just now. The total background flux of 1.7 counts per second is about the same as what's in the field of view, the collimator, which is somewhere in the order of 1.5 to 1.7. Of that 1.7 that we attribute to the background, about half of that is through the collimator and the other half is backscattered off the back of the detector. The bottom line is we're getting high spatial resolution. The model calculations you're making don't hold up.
Right. Well, it'd be good if you could explain why.
I think it's your job to explain why your calculations work. They don't.
I've got a question too, Bill, don't leave yet.
Okay.
I understand the spatial resolution differences between the two instruments. Can you say any, or give any comment on whether the two instruments are also looking at the same depth?
Yes, absolutely. The depth to which from which the neutrons come is a function essentially of the physics of what's going on in the surface, and we're all sensitive to the same energy range of neutrons that are produced by the same processes. It's just a difference of, in one case, you're averaging over a very large area, the other case, you're averaging over a smaller area.
Okay, thank you.